Hello. In the previous video, we derived the infamous Rayleigh-Jeans law and saw how the ultraviolet catastrophe came into being. In this video, we shall find out how Max Planck, a German physicist, solved the problem by using a rather unexplained assumption. But before we dive into this topic, I would want to recap what we did previous time. Right? So we found that the energy density of a black body, that is the energy per unit volume of a black body at a given temperature and frequency, was given as follows. The energy was given as a function of energy density. Now rho v is the energy density and dV is the differential energy volume. Right? Energy density and dV is the differential volume. Was equal to 8 pi mu squared by c cubed kBt into dV. Now this term referred to the number of electromagnetic radiators or the number of modes in frequency range mu, mu plus d mu. This referred to the number of modes in mu, mu plus d mu. And this term referred to the average energy of each mode in this frequency bandwidth. This was the average energy of each mode. And dV as usual referred to the volume. Now this formula gave us a drawback of energy being proportional to mu squared, and energy shot up to infinity as mu increased, particularly in the UV region. Now this was done in around 1900. So before the era of Max Planck, let us find out what were the results that was already available to him and how he arrived at a feasible solution. Now one thing he already knew was the phenomenon of photoelectric effect. Now in the briefest of terms, photoelectric effect was first performed in around 1886 by a physicist called Henry Hertz. Now what he did was he took a piece of metal and shined ultraviolet rays onto it, collimated beam of ultraviolet rays, and found that and he kept this in a say a potentiometer or a voltmeter, and he found that the potential was developed across the system, and with this he could conclusively state that electrons were emitted from the metal. So as ultraviolet rays were as they strike the metal, electrons were emitted from the surface of the metal. Now, according to what was fantastic about this experiment was, according to classical wave theory, the kinetic energy of the electron emitted should be proportional to the intensity of the incoming rays, and intensity of any wave is proportional to its amplitude. If you have a wave given by phi equals a sine omega t plus phi, where phi is some phase angle and omega is its angular velocity, if this was an equation of the wave, then the intensity of the wave should be proportional to a squared, and then energy should be proportional to intensity. But what he found was energy was totally unrelated to intensity, and rather energy was proportional to the frequency of light. Say if we increase the frequency from say ultraviolet to X-rays, then energy of the emitted electron was increased, and this energy was physically measurable using a potentiometer. Again, if we reduce the frequency to say almost blue light, again the energy would have reduced, right? And one more interesting conclusion he arrived at was that the light intensity affects only the number of electrons and not the kinetic energy. So intensity affected only the number of electrons emitted and not the energy of each electron, right? So from the experiment of photoelectric effect, it was somehow known as that if you have energy versus frequency plotted, you have somewhat straight line. Now one more point for quantization we already have was in a previous derivation for waves in a box. We found classically it is said that the energy of a wave is in its electric and magnetic fields. Now if we reconcile the given picture with classical waves, and we already found that you can have waves only which have where their amplitudes are 0 at the ends, and the electrons can only have wave numbers or wavelengths such that n lambda by 2 was equal to L, where this was L. And if lambda was the wavelength of the wave, then this were the only allowed wavelengths. And from wavelength, this implies you have NC by mu 2 equals L. This implies mu was equal to NC by 2L, where C was the speed of light and L was the length. So if you had a box of a given length and only a given set of frequencies based on N, where N is a integer, could have been possible. So these were a set of evidences which were already available to Planck. And then he moved on from this and did some, and just had this basic assumption in mind. So Planck put this assumption on paper and just went through with it. He assumed that the energy was proportional to mu and considered a constant which we now call h, or the Planck's constant, called it h mu. Now this was the energy associated with each photon of energy mu. There was no concept of a photon, so we considered it as a mode of waves. So a mode has the energy. A mode has with frequency mu has energy h mu. And if the mode consisted of say n photons, the energy would have been n times h times mu. Right? So this was the energy formula considered by Planck. We now consider all the modes or all the photons that had to be in thermal equilibrium. Till now we have only considered about one photon or one mode of particles. Now we shall consider the set of all modes available, and then we impose the condition of thermal equilibrium, say at a temperature T. Now in order to establish this equilibrium, there must be certain ways of exchanging energies between the modes. Say this is one mode where you have zero values of amplitude here. This was another mode. This was the third one, and so on. There was some way of exchanging energy between the modes or electrons, and this can only occur through interactions with any particles or oscillators within the volume or within the walls of the enclosure. Now what he used, Max Planck used, was something called the Boltzmann distribution. Boltzmann distribution. I'll attach a link for a useful resource on Boltzmann distribution. But basically what the Boltzmann distribution gives us is the probability that a system, say if you have, okay, I'll just write it down. This gives us now the Boltzmann distribution basically gives us the probability that a system will be in a certain state S, and that probability is a function of the state's energy and the system's temperature. To give a better analogy, say you have a discrete set of states available, that is S1 to Sn. A particle belonging to the system can be in any one of these discrete n states, and each state has an associated energy E1 to En, and the whole system is at thermal equilibrium at say temperature T. Then the Boltzmann distribution gives us the probability that the state of the particle is Si, that is I amongst, where I belongs to 1 to n, as a function of the energy of the state, energy of each corresponding state, and the temperature of the system. Let me call this T-sys system, as a function of the energy of the state and temperature of the system. Now this function was actually the exponential function, the exponential of minus Ei by kBt, where kb is the Boltzmann's constant, right? So now if I considered if you consider the probability that a single mode has say energy En is equal to n h mu, then using the Boltzmann distribution, you have that the probability that the energy is En will be equal to exp minus En by kt by summation n is equal to 0 to infinity exponential of minus En by kt. The denominator just acts as a normalizing factor so that the probability is between 0 and 1, right? Now our goal right now is to find the mean energy of the mode of frequency. That is, here we found out that the energy density was as a function of number of modes in volume in a frequency bandwidth mu comma mu plus d mu, and the energy per mode was on average kBT. This was derived classically. Now with this new assumption that energy proportional to frequency, we want to find such a term. Right? Now if you have the probability of energy of say En, of probability energy being En, then the average value of energy is defined as summation as En to P of E is equal to En, where N is equal to 1 to infinity. Just this is a simple postulate used from statistics, where if you have a set of states I to n, then the average or the expectation of the variable En is given by summation over each energy value into its probability value. Now this will be summation En exponent of minus En by kt by summation exponential of minus En by kt. Right, so n is equal to 0 to infinity, n is equal to 0 to infinity. Now En, we've hypothesized En to be n times h times mu. Right, n times h times mu. Now we use the formula for En here. So the average value of energy will be summation n times h times mu exponential of minus nh mu by kt by summation exponential of minus nh mu by kt, summation from n is equal to 0 to infinity. Now let's make a clever substitution. Looking at the conditions, let x is equal to exponent of minus h mu by kt. That virtually acts as a constant, so I don't need to write that again and again. So I can take h and mu out of the summation brackets because they're independent. Summation n times, notice that this is exponential to the power of minus n, and n minus is seen there, so you have n x to the power of n by summation x. Right? Oh, I'm sorry, x to the power of n. So this is my equation till now. So I'm just going to expand this and see what I can do. So x is equal to, so from n is equal to 0 to infinity, n is equal to 0 to infinity. Now when n is equal to 0, the numerator becomes 0 into 0. Then when n is equal to 1, you have x. N is equal to 2, you have 2x squared, 3x cubed, and so on. Similarly, in the denominator, we have n is equal to 0, it is 0, n is equal to 1. It is x and x squared, x cubed, and so on. Notice that I can take x common in the numerator, so I'll write that as follows. Now the average value of energy will be h mu times x times 1 plus 2x, 1 plus 2x plus 3x squared, blah, 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 by 1 plus x squared plus. Now we use two useful results from arithmetic, that is 1 by 1 minus x will be this expansion. So the denominator summation is equal to 1 by 1 minus x, and 1 by 1 minus x squared will be equal to 1 plus 2x plus 3x squared, and so on. These are results from arithmetic and can also be derived. You just consider a geometric progression, and then you take the summation of geometric progression and you arrive at this. If I use these two results in this given equation, and I have E is equal to h mu x times, this becomes 1 by 1 minus x whole squared by 1 by 1 minus x. 1 by 1 minus x gets cancelled. It's equal to h mu x by 1 minus x. Now if I divide numerator and denominator by x, so it's cancelled. So this is h mu So I divide this 1 by x minus 1, right? Now this is equal to h mu by x to the power of minus 1 minus 1, and x, what we used for e to the power of was exponential minus h mu by kt, right? This was the x we used. If I substitute that in this, I have E is equal to h mu by e to the power of h mu by kt. Now minus and minus cancels it, minus 1, right? So now we have found that the average energy is h mu by e to the power of h mu by kt minus 1. Now this is the result we've been seeking. Now we're not done yet. We need to find the classical limit, right? So classically we found that the limit is from the law of equipartition of energy. We found that the energy of each mole should be kBT, right? Now let us try to find out what this value of E gives us in a classical limit. Now energy of n photons with frequency mu was nh mu. So we had a minimum. A photon can have an energy minimum of h mu, right? Now let's see the classical limit of this. To find the classical limit, we allow the energy quanta h mu to tend to 0. That is h mu to tend to 0. That is we are allowing a minimum for the energy to exist. Allowing a minimum of energy, right? So we expand the denominator for small values of h mu by k, right? So you have e to the power of h mu by kt. This is an exponential minus 1. So this will, expansion of e power x will be 1 plus x plus 1 by 2 factorial. So I'll just write the first two terms, whole square, blah blah blah. Then you have the minus 1 from this, minus 1, 1 gets cancelled. Then you have h mu by kt. So let's ignore these terms because they're too small. This becomes 0. So average value of energy when you consider the classical limit, h mu, and this gets cancelled and voila. Thus, for small values of h mu by kt, as h mu tends to 0, the classical limit E becomes equal to kt. Thus, if we take the classical limit, we recover exactly the expression for the average energy of a harmonic oscillator in thermal equilibrium. That is, E bar is equal to kt. Now we can now complete the determination of Planck's radiation formula. We've already shown that the number of modes in this frequency bandwidth mu comma mu plus d mu is 8 pi mu squared by c cubed. If we use that relation, then rho of mu dV will be 8 pi mu squared by c cubed E bar by dV. This is 8 pi mu squared by c cubed into 1 by e to the power of h mu by kt minus 1 into dV. Now this is the Planck distribution formula. Planck distribution formula or functional, both are possible, right? Oh, I think I must have h mu here. So this was the formula given by Max Planck, where he considered the assumption that energy is quantized and arrived at this other expression. Now one thing we notice here, that this function has the same mu squared but also has a h mu by e power h mu by kBt. So mu comes here as well. Now if you try to plot this function as a function of mu, if you plot the energy density, the energy is a function of temperature and frequency was this, we have an initial rise as mu squared increases, and then exponential 1 by e power x, right? That brings the function down. So you have an increase, then you have a decrease here. So at higher values of mu, the value e power h by e power h mu, the exponential function, drastically reduces this value, right? So thus the Planck's equation is a combination of an increasing function and a decreasing function, making, you have a maxima in the middle due to the combination of increasing and decreasing function. And thus Max Planck in the year 1900 gave us h mu, or with his assumption that energy of a photon is equal to a minimum of h mu, or is an integral multiple of n times h times mu, where mu is the frequency of the photon. So now the energy of the photon was discrete and not continuous. It was not a continuum, it was discrete, right? And this discrete nature of energy further gave rise to quantum mechanics. So welcome to the world of quantum mechanics. Thank you.